and we will also prove it when we actually do the experiment. So here we have my little equation. So the equation for change in temperature is Kmi, which is the constant for the solvent, which in this case is water, and we're doing the freezing point, which at just pure water is 0 degrees Celsius. So the K, which is the constant for water, the freezing constant, is a 1.86. M stands for molality, which is moles of the solute over kilograms of the solvent. Now we have placed the various solutes in their own separate cups, but each of the cups is filled with 0.3 kilograms of water in it. So, in this case, in the experiment, I'm dealing with table salt. Just an example, I'm just going to give an example using table salt. I put in 0.01515875 moles into the solution. Now, I've kind of messed up here and I didn't proportionate it right. But also you have I, which stands, I don't know, I like to call it stands for ions. Because you're basically deciding that you want to disassociate. When it disassociates itself in solution, and you want to see how many ions it forms when it goes in. So you take table salt, for example, which is NaCl, and when disassociating itself in water, it becomes into 2 ions. And it becomes into 2 ions, and so the I value would be 2, because it disassociates into 2 ions. Now if you take table salt, or table sugar, for example, C12H22O11. Now, you can tell from that molecular formula that it is not going to break apart into ions. It will be one single molecule. It's not going to break apart. So the I value will be 1. But in this case, since we're dealing with table salt for this example, I'm going to say it's 2 because it breaks apart into 2 ions. Now, you simplify this equation and you get the change in temperature, or delta T, is equal to 0.18798685. So, meaning that there's a change, that there should be, mathematically, a change in the temperature from 0 degrees Celsius. And so, because it says that it lowers the freezing point, you subtract it, which means that the freezing point of the new solution should be negative 0.18797 degrees Celsius. Now we shall see what happens when we actually freeze it. Now, when dealing with boiling point, the standard boiling point for water would be 100 degrees Celsius. Again, we use the same equation, same formula. It is still a change in temperature. But the constant is changed. The constant for boiling, which I have not put on here, but it's K subscript B. Now the K subscript B, so the constant of boiling for water is 0.52. So I plug in the same molality for the equation, because I'm still using table salt for this equation, still using table salt for this example, and I plug in the same value for I, which I have proportioned it out so I can include it on this line. And so you have the molality here, and you multiply by the 2, and you have the constant. So the only thing that really changed is the constant. So you multiply it all out, and you get the change in temperature, or delta T, is equal to 0.05255. Now, because of colligative properties saying that there should be a raise in the boiling point, so meaning that you would add this to the original boiling point, so meaning that the boiling point of the new solution should be 100.05255 degrees Celsius. That's what should happen. We will see what happens next. So after we finish freezing the solutions, which we do in process right now, we will then boil the solution and get the temperature, and we will repeat the experiment 2 more times. So we have 3 sets of data to compare to the mathematical formulas, which should be going on. Now, of course, we are humans, and humans make errors, and there's also mechanical errors. So we will also determine the percent error, and hopefully it is within a reasonable margin, so we can safely say and prove that colligative properties is in fact true. So I believe, yes, Jeeves, okay, yes, Jeeves has just concluded with me that the solids, or the solutions have, pardon me, begun to freeze. So you can go ahead and run along with him and watch and go and see what the resulting temperatures are. And then I will see you back for boiling, and I might see you in between, you know, a little bit, so I can show you what should happen for the other two solutions when it freezes and boils. So go ahead and run along. Bye bye. Alrighty, so now we're going to check it and see whether they have froze yet. And taking a look at this, I see crystals on top. It is starting to freeze, and the temperature is 30.9 degrees Fahrenheit, because I'm using a thermometer that's customary. And as I look at the other ones, none of them seem to be crystallizing at all. I mean, they're just still water. So none of them is starting to freeze yet. So the sugar solution is starting to freeze, and it is frozen at 30.9 degrees Fahrenheit. And that is 1.1 degrees Fahrenheit below the freezing point of water. So that's already proof that the adding the sugar has changed the boiling and the freezing point. Next, we're going to do the boiling point, but we're going to come back when the other two solutions have frozen. Alright, I'm just going to check the solutions again, and the baking soda solution seems to have gotten slushy. It's starting to crystallize and freeze. So let's check the temperature real quick. Yowzers, it is 26.8 degrees Fahrenheit. That's pretty cold. And that is 5.2 degrees colder than when water freezes, so that's pretty cold. Alright, we're going to check the last remaining solution, the sodium solution. And it's gotten nice and slushy and starting to freeze. And the temperature is 23.2 degrees Fahrenheit. Man, that's almost 10 degrees more. That's, wow. Now, this is prime example of the colligative properties. We're just going to go ahead and go straight into the boiling section. So we're going to boil this and see, because we know automatically now that colligative properties, that when you add a solute, it does indeed change the freezing point and it lowers it. But now we're going to go test and see whether it raises the boiling point as well. So